Hey everyone. I've been out of the loop for a while. We are getting close to. Wait a second. I have the video. Yes, I do. We are getting close to start classes, and I've been kind of focusing on having my courses ready. Um, I think my latest one is to realize that I'm teaching a course that I taught before, but using a book with all the uh, good things publishers give you. And since I'm using free sources, I have to find parts of the book in different places and put that together and create assessments. And that took me a while, um, but it's done. So I've seen a lot of communication going on. Vike is doing a lot of reading and putting up notes. I haven't gone there yet. I saw Shaunak put mail with his veiling determination, which seems to be fine. I will look into more details after I'm done with this taping. And then Ognian put a question regarding veiling. Shaunak's reply seems to be correct. It is correct, I mean, and I would like to expand on that because it has some learning curve for all of us, is for me to remember details of all of that. And since my daughter gave me an iPad Pro, a mini one, but it's an iPad Pro, I will try to sync um, with my computer and kind of a write on it, like as a tablet. And so I'm using this to learn to operate this stuff too. But um, let me get my iPad. And I would like to go on exactly this subject. And I think for doing that, I have to share my screen. And I have to come here. There you go. It should be coming, I think. There you go. And then I get my annotation. There you go. So basically, let me take this off for now. I think I need that. But anyway, so um, just reviewing the concept of veiling. So if you have a star, this star will have a flux emission. Let's say the star is a T-Tauri star, so we are dealing with a cool stars. Effective temperature is 4,000 Kelvin, and then we can approach the flux distribution of this star by a Planck function. So let's say the star has distribution that is one of a 4,000 Kelvin. And then the flux that would come from this star would be, according to Stefan Boltzmann, 4 pi times the radius of the star square times um, the emission, the flux emission, or the flux distribution of a typical 4,000 Kelvin star. But if in addition we add a spot, and this spot has this spot has, let's say, a temperature I'm making up, 10,000 Kelvin. So, and assume this spot is optically thick, it can be approached by a Planck function, then we would have this equivalent distribution, and the flux that would come from the spot 4 pi. This is the tricky part. So how are we going to address that part? So the best way to do, and in fact people usually do that, it's a first approximation, it's just a rough approach, is to say, okay, this spot has a fraction of the area of the star. So the area of the spot, so the area of the spot would be a fraction of the area of the star. Let's say 10%. So which means when you look at the star, of course it's a 3D thing. So we have a sphere, and we see that sphere projected along a plane. So, but we say, okay, of what I see, there is a projected area whose fitting factor is f, 10%, 20%, 15%. And then you would say the flux that comes from the spot is the area of the spot, right, times the Planck function of the spot, and that would give us f area of the star times the Planck function of the 10,000 Kelvin. So basically, when you think about observation, so the flux that is observed is equal to 1 minus that area, right? 1 minus that area that is being filled up by the spot times the Planck function of the photosphere plus the area that is being occupied by the spot times the Planck function of a, let's say, 10,000 Kelvin. So this would be the observation that comes out of the star. Now let's think about veiling and try to relate those things to veiling. So what is the veiling? And I think I did this before, but I will repeat it. So let's say you have a star that, and the way we measure veiling, we say, okay, the star has a photosphere that is well behaved, and the photosphere can be approached by a template. So the template has a photosphere or photospheric distribution that I'm calling F for F photosphere, and so it's something that goes like this, let's say, and we say that this flux is being added by some external emission that comes from the veiling, right? So and the veiling we measure is a multiplicative factor of the photosphere itself. So is V times F full. So that's what we measure. So basically, what comes out of the system is what comes out of the photosphere plus a factor of how much the photosphere altogether is sending out to space, multiplied by a number that we are calling veiling. So that's how we set veiling. So it's pretty much 1 plus V multiplied by the flux photospheric. And this is what we observe. This is basically what we observe. Okay? So what we observe is what comes from the photosphere itself, that in my outline is all of this thing here. minus minus the spot itself, and the spot flex, the continuum that comes from the spot. We are saying, well, it's certain number, so some factor that multiply the continuum photosphere in a particular wavelength. So all of this is wavelength dependent, right? So it's for a very specific color, and that's what we got. So we have a flux observing here, as seen from the veiling aspect of this problem, and we have a flux observing that is coming from the physics of it. So we have two distinct regions, each one with some Planck function associated with it. So if you want to do a better job, like we did in a previous paper, previews from the paper that we published with Sylvia, we use a code to generate this flux distribution. We use a code called Cloudy. This was developed by a French person, forgot his name, and it's very nice. Perhaps later we might put our hands on it, but basically we have this quantity here. This quantity, we can associate them to one another this way. And if we associate the flux photosphere with a Planck function, that's a very crude approximation, which is what we are doing here, right? Then our then 1 plus v is equal 1 minus f plus f that multiply b index 10,000, b at index 4,000. And then we can simplify 1 here, and then v dividing, wait a second. Yeah, veiling is going to be f that multiply the 10,000 divided by the 4,000, right? Minus 1. Okay. Now, let's bring now into perspective and see how this function should behave in IDL. My computer's taking forever. Okay. So we take B 4,000. So let's create a wavelength array. So 1,000, 1,500, 1,500, 2,000, 1,500, 1000. Should do it more clever, but sorry. 3000, 4000, 1000, 6, 7, 8, 9, 10, right? And then B 4000 is equal this. There is a embedded Planck function in IDL. You enter the W array and the effective temperature. The array has to be done in angstrom. And B, which one? 10,000 is equal Planck W 10,000. And then we want to plot W and Veiling, right? That's what we have been done with the measurement of Veilings done in our data. So W times Veiling, but the Veiling is a filling factor. So let's take a filling factor, assuming this accretion region, the spots is, let's say, 10%. You tell me. So 10% is 0.1 times B 10,000. That's the equation. That's the equation that comes from here, right? F B 10,000 divided by B 4,000 minus 1. And then we close this up. We want to put that in a range from 3,500, oops, to 8,000. That's the optical range we are working. And the veiling we calculate is always have a Y range that goes from 0 to, let's say, 3 or 4. PS equal -2. Oops. Too high over the PS, let's say veiling 10. Now you see how this quantity goes wild in the blue range. I mean, you could try different combinations. For instance, can we do this more? I think we can. We could, for instance, go here, Planck. Let's change the temperature and of this spot and put 8,000, right? 8,000 W divided by Planck 4,000 W. So now I'm putting the function there, and so if the spot has a mild temperature, not 10,000, but is 8,000, then what we got? What did I do? Oh, I did it. Plot W. I think I made the substitutions in the wrong place. So this is Planck 10,000. No, I said 8,000, right? 8,000 W divided by the Planck. I'm doing the same thing I did before, except that I inputting I'm changing the temperature of the Planck function. Instead of it being 10,000, I'm putting 8,000. And what? What? Oh, I did it wrong. Wait a second. Yeah, sorry. I have to enter the wavelength first, and then the effective temperature, the wavelength first, and the effective temperature. And I still have error. Man, what is going on? Okay, I don't need that. Wavelength first and effective temperature after. Legal operand. Oh, I cannot operate with the function? I didn't know that. I cannot divide function. Okay, sorry about that. So I want to be fancy, but I think I can. Okay, so let's do 8,000 and 8,000. $4,000, and I want to do 8,000. Right. 8,000. Okay. So and then I can do this 8,000, and I get nothing. What's going on here? B 8,000, B 4,000. My iPad is complaining about something. I don't know what's going on here. 8,000, 4,000 is float, is giving numbers. It's not giving anything. But if I put 10,000, it gives results. So I don't understand. No, now it's not giving anything. What's going on? What is going on here? Unless you want to make W float array. Wait a second. We don't like that either. Make this real, 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 and real. B 4,000 Planck, W 4,000, and B 8,000, 1,000, 8,000. Now I didn't have that error. I think it was complaining that I was entering integers. Now I can do my plot, not at 10,000, but 8,000. 8,000, yeah, that should do. There you go. Right, so I can reduce the filling factor even more. So if instead of a 10% of the stellar radius, but it's 5%, right? And then I have valence that approach more to the ones we are having in our data. And if we fudge the temperature, so here's the thing. Here's my whole hope when I start, and why did I try to why I try to invest so much time in getting the data in the blue, because here in the red part of the spectra, the valences are going to be low anyways. But depending on how it rises in the blue, we can use that information to constrain the temperature of this accretion region in the photosphere, but also not only that, but also the filling factor. Well, what is the percentage of the area in there? So we could try to tackle both if we can use some chi-square feature, right? To see on a range of possible models which one match the best combination of filling factor and effective temperature for the spot. But I don't think we can go there because the scattering is too large in that region. But if we apply for good data, or if you find good data in the blue, we might be able to try to assess that. All right, okay. So I will start replying the emails now by process this data, this video here. Okay, bye.